Out in the vast expanse of the cosmos, amidst the grandeur of swirling spiral galaxies and massive elliptical giants, exists a population of celestial objects that are small, yet significant dwarf galaxies. These galaxies, though diminutive in size, are scattered throughout the universe and come in various shapes and compositions. These diminutive stellar systems, as their name suggests, are significantly smaller and less massive than their larger counterparts. They can be found orbiting larger galaxies or floating alone in the vastness of space. Don't let their size fool you. Dwarf galaxies are intriguing cosmic entities that hold crucial clues to the universe's formation and evolution. Their simplicity compared to larger galaxies makes them ideal subjects for studying the fundamental processes of galaxy formation. Dwarf galaxies are defined as galaxies containing up to a few billion stars, a paltry number compared to the hundreds of billions of stars found in galaxies like our own Milky Way. This smaller number of stars means that dwarf galaxies often have less complex structures. Their smaller size results in lower gravitational pull, making them more susceptible to the gravitational influence of their larger galactic neighbors. This interaction can lead to fascinating phenomena such as tidal stripping, where stars and gas are pulled away from the dwarf galaxy. Their low surface brightness, a consequence of their sparse stellar populations, makes them challenging to detect. Many dwarf galaxies remain hidden in the shadows, only discovered through meticulous observation and advanced technology. Yet, despite their diminutive stature and elusive nature, dwarf galaxies play a crucial role in our understanding of the universe. They are often considered the building blocks of larger galaxies, merging over time to form more massive structures. They offer a unique window into the processes of galaxy formation, the distribution of dark matter, and the chemical evolution of the cosmos. By studying dwarf galaxies, astronomers can gain insights into the early universe and the forces that shaped the galaxies we see today. The realm of dwarf galaxies is not monolithic. It encompasses a diverse range of morphologies and characteristics. These small yet fascinating celestial objects come in various forms, each with unique features that tell a story about the universe's history and evolution. Astronomers classify dwarf galaxies into various types based on their shape, stellar content, and star formation activity. This classification helps scientists understand the processes that govern galaxy formation and evolution, shedding light on the complex dynamics of the cosmos. Elliptical dwarf galaxies, often found orbiting larger galaxies, are characterized by their smooth oval shape and lack of recent star formation. These galaxies are typically composed of older stars, and their smooth appearance suggests a history of little to no recent interaction with other galaxies. These ancient systems are thought to be remnants of early galaxy formation, their gas and dust long since consumed. The lack of gas and dust means that new stars are no longer being formed, leaving behind a population of old stars that provide a glimpse into the early universe. Irregular dwarf galaxies, on the other hand, are a hotbed of star formation. These galaxies do not have a defined shape and are often chaotic in appearance, with regions of intense star formation that light up the galaxy. These chaotic systems, often found in isolation, display irregular shapes and are rich in gas and dust, fueling the birth of new stars. The presence of gas and dust clouds indicates ongoing star formation, making these galaxies vibrant and dynamic. Spheroidal dwarf galaxies, as their name implies, exhibit a spheroidal or slightly flattened shape. These galaxies are typically found as satellites of larger galaxies and are thought to have been shaped by gravitational interactions with their larger neighbors. They are often found as satellites of larger galaxies and are thought to be remnants of tidally stripped galaxies, their outer layers ripped away by gravitational interactions. This stripping process leaves behind a dense core of stars, which we observe as a spheroidal dwarf galaxy. Adding to the diversity are ultra-faint dwarf galaxies, the faintest galaxies known. These galaxies are so dim that they are challenging to detect, even with powerful telescopes. These extremely low luminosity systems are composed of old, faint stars, and are thought to be some of the oldest galaxies in the universe. Studying these ancient galaxies provides valuable insights into the conditions of the early universe and the formation of the first stars and galaxies. Dwarf galaxies, often found in close proximity to larger galaxies, engage in a delicate gravitational dance with their massive companions. These interactions shape their evolution and leave telltale signs of their intertwined history. Acting as satellites, dwarf galaxies orbit larger galaxies, their paths dictated by the gravitational pull of their massive hosts. These orbits are often irregular and can be significantly influenced by the distribution of dark matter in the host galaxy. The gravitational interactions between dwarf galaxies and their larger companions can have dramatic consequences. Tidal forces can distort their shapes, stripping away stars and gas, leaving behind streams of stellar debris that stretch across vast cosmic distances. These interactions, while potentially destructive, can also trigger bursts of star formation in dwarf galaxies. The gravitational jostling compresses gas and dust, igniting the birth of new stars and shaping the evolution of these small galaxies. Section 4. Dark Matter Laboratories. Dwarf galaxies, despite their seemingly insignificant size, play a crucial role in one of the biggest mysteries in modern astrophysics, the nature of dark matter. These small galaxies, often overlooked in the grand scheme of the cosmos, are actually treasure troves of information. They provide a unique window into the unseen and enigmatic components of our universe. These diminutive galaxies serve as cosmic laboratories, offering unique insights into this elusive substance that makes up a significant portion of the universe's mass. By studying them, scientists can gather data that is otherwise difficult to obtain from larger, more complex galaxies. The simplicity of dwarf galaxies makes them ideal candidates for such research. Dark matter, invisible to telescopes, interacts gravitationally with ordinary matter, its presence inferred by its gravitational effects on visible matter. This gravitational interaction is a key method by which astronomers detect and study dark matter. Without emitting, absorbing, or reflecting light, dark matter remains hidden, yet its influence is undeniable. Dwarf galaxies are particularly rich in dark matter, with their outer regions rotating much faster than predicted by the visible matter alone. This unexpected rotational speed is a clear indicator of the presence of dark matter. The more we study these galaxies, the more we learn about the distribution and behavior of dark matter. This discrepancy between observed rotation and predicted rotation, known as the galaxy rotation problem, provides strong evidence for the existence of dark matter. The galaxy rotation problem has been a cornerstone in the study of dark matter, prompting numerous theories and models to explain this phenomenon. Dwarf galaxies, with their high dark matter content and relatively simple gravitational systems, offer ideal environments to study the distribution and properties of this enigmatic substance. Their simplicity allows for more straightforward analysis and modeling, making them perfect subjects for dark matter research. By observing the motions of stars and gas in dwarf galaxies, astronomers can map the distribution of dark matter and test different theoretical models of its nature. These observations are crucial for refining our understanding of dark matter and its role in the universe. These studies provide crucial clues to understanding the role of dark matter in galaxy formation and the evolution of the universe as a whole. As we continue to explore and analyze dwarf galaxies, we move closer to unraveling the mysteries of dark matter and its profound impact on the cosmos. Section 5. Stellar Nurseries in the Void. While some dwarf galaxies exhibit quiescent stellar populations, others are teeming with star-forming regions, actively giving birth to new generations of stars. These stellar nurseries offer a glimpse into the processes that govern star formation in the early universe. Irregular dwarf galaxies in particular are known for their vigorous star formation. Rich in gas and dust, the raw materials for star formation, these galaxies provide the ideal conditions for the gravitational collapse of gas clouds, leading to the birth of new stars. The relatively low metallicity of dwarf galaxies, a measure of their abundance of elements heavier than hydrogen and helium, also contributes to their active star formation. Low metallicity gas cools less efficiently, promoting the formation of dense, star-forming clouds. The study of star formation in dwarf galaxies provides valuable insights into the processes that shaped the early universe, a time when galaxies were smaller and less enriched with heavy elements. By observing these stellar nurseries, astronomers can piece together the history of star formation and the chemical evolution of galaxies over cosmic time.